Hello, in this video I'm going to talk about cycloaddition reactions. In cycloaddition reaction, we have two pi bonds converting into two new sigma bonds. So for example, we could have this pi bond moving there to create a new sigma bond, which prompts this other one to move to that location, which creates a new sigma bond, and it prompts this other one to move over there. So the pi bond which remained has moved the position, and then we have two sigma bonds. Okay, so here we say that we do have 4 plus 2 cycloaddition because we have 4 pi electrons from the diene, and then the 2 pi electrons from the what we call the dienophile. Okay, so whenever we have a reaction of this nature, we call it a Diels-Alder reaction. Diels-Alder reactions usually happen faster when the dienophile has an electron withdrawing group attached to it. So the diene is the one that's going to be acting as the nucleophile, and the dienophile acts as the electrophile. So some of the electron withdrawing groups that could be attached include an aldehyde, a ketone, an ester, or we could have a carboxylic acid or a nitrile. Okay. The other factor that do affect these reactions is the diene structure. The diene structure, if you look at the diene, it needs to be in S-cis conformation. So if the starting material is already pre-organized in the S-cis conformation, like in this case cyclopentadiene, then the reaction will actually happen even at room temperature. However, if you do have a compound that is in a fixed S-trans conformation, then it does not matter even if you use a good electron withdrawing group attached to the dienophile, there will be no reaction. Another factor that affects these reactions is the formation of the bicyclic systems. So if we have a case where we are forming a bridge, so we have the small bridge here, and then we have this other, one of them is the large bridge, the one that has the pi bond, and then there's another bridge over here. So if in the process of the reaction, the dienophile organizes itself so that the dienophile has the electron withdrawing groups being on the same side with the developing pi bond, then that kind of reaction is going to be favored because the interaction between the electron withdrawing group and the developing new pi bond is favorable, being on the same side. If they are on different sides, then it does not influence the reaction to go faster. So the minor product will be the exo, the endo is going to be the major product. The other factors involve temperature. If very high temperature is used, then the high temperature will actually favor the reverse reaction. That's because this reaction, if you look at it, we are moving from a high degree of freedom to a low degree of freedom. So entropically, at higher temperature, it's going to favor the reverse reaction. But usually this happens mostly if you do the reaction at greater than 200 degrees C. So up to 90-100 should just be okay for the Diels-Alder reaction. The radioselectivity is also a factor where there are cases where you could end up forming two products. And if that happens, we need to look at which one is going to be the major one. So like here, the diene is attached to an electron donating group. The oxygen here can donate electrons to the diene. Okay, so when that happens, it actually helps the reaction to go faster. So if we push our arrows the way we were doing before, what we are going to have is this goes here, then we create a new bond. This goes here, we create a new bond. This goes here. So that's going to look like what we have over here. But remember, this compound is flexible, so it could also reorganize itself into this format. So that way we can end up forming the major product. Why is it the major product? The bulky groups, the methoxy group and the carbonyl, are on direct opposite sides of each other. We call those ones the para position. Now these are very close to each other, so there is some kind of steric effect. So the one that experiences the less steric effect is going to be the major product. Let us look at the stereoselectivity. In some cases, you could have compounds that are cis, that is, compounds on the same side. Similar compounds, well, similar substituents in this case, on the same side. And if that happens, the reaction will go on, and you end up with the same substituents being on the same side when the stereochemistry is now achieved. Okay? If those groups, those similar groups, are on different sides, okay, they are kind of trans in this case, then we're going to end up with the same compounds being on the opposite sides to each other, and of course that will also create an enantiomer. Okay? Triple bonds are also able to undergo Diels-Alder reaction. So just do the same thing. Create a single bond here, prompts this one to create a single bond here, and that moves to that position. So we're going to be left with a double bond. So you can see the double bond here. So there's no stereochemist in that position, so we end up with a product. Okay, thank you for watching and have a good one.